Here we are one last time talking about Newton's first law. We're talking about, first of all, let's look at the weights here. These are 4 bricks, equal size bricks, equal mass, and they are held up by scales. This one has 3 scales and 3 ropes holding it up. This has 1 rope and 1 scale, and 2 scales with 2 ropes, and 2 scales both attached on the same rope holding up. Now, the question is, which of these will have the greatest tension on the rope? The more ropes that are attached to an object, that means that the force of the object, let's just say these bricks weigh 10 newtons, okay? And that means when there are 3 different scales, the weight will be split evenly between these. So we would have 3.3 here, and 3.3 here, and 3.3 here. And so the weight would be scattered across those 3 ropes. All right. If there are 2 ropes like this, then each one would have to pull upward with a force of 5 newtons, because we know that the weight of the brick is pulling down at 10 newtons. So these would have to pull up as well as the 10 newtons pulling down, canceling out, and having it a net force of 0, and therefore the thing is just hanging there. If there is 1 rope, then we know this rope has a tension of 10 newtons. Okay, because there's a force of 10 newtons pulling down on it. The rope is pulling up with 10 newtons, and therefore the net force is 0, and the brick will stay suspended, hanging on the rope. All right, now when you have this one, you still have 10 newtons pulling down on it. And since you have 1 rope, it would also be 10 newtons pulling up. Okay, now if the second scale weighed more, then you could argue that there's a greater mass hanging on it because of the number of scales. But we're not really considering the mass of scales in this, so we're not going to worry about that. So basically, we would say which rope has the greatest force or tension on it. It would be B and D equally. They both have 10 newtons of force acting on it, or putting tension on the rope. Whereas these other ones, the 2 have split it in 5 apiece, and then 3 and a third, 3 and a third, and 3 and a third. Give or take a little bit, so it comes out to 10. All right. Now, a similar kind of situation would exist if you were, like the boy here, on the scales. If he's hitting both scales, let's just say that the boy has a mass of 200 newtons, which is only about 50 pounds, so that's pretty light. Okay. And if he's standing on both scales equally balance his weight, then we would expect one scale to read about 100. And the other scale to read about 100. And if you put those 2 together, then you have a force of, they would be pushing up with a force of 200 newtons. His weight would be pushing down, and we would have a net force of 0, which is why he's standing there. Now, if he leans over on one side, he's still pushing down with a net force of, of 200 newtons. His weight stays the same. However, we would expect this side maybe to go up to, say, now it has 150 newtons because he's putting more weight or more force on that side, whereas this side might only have 50. But notice that the total amount of force is still the same. So we have a 200 Newton force pushing up, 200 Newton force pushing down, and we still have a net force of 0 in our equilibrium. All right. There are other examples. If we look at the girl hanging from a pulley, once again, she has 2 ropes that are supporting her weight, and so her weight would be half on one and half on the other. If she had a scale here, it would measure the tension on this one side, and it would be half of her weight. All right. We could also do the same thing with someone swinging on a trapeze. As long as it's equal, then each of these ropes would have a tension that would be equal to half of the weight of the girl. If she leans harder on one side, then we would expect it to be more than half. But the total force on the 2 ropes would add up to the weight of the little girl. All right. Now, if we go off one last thing, a couple things. Let's look at let's get one more real quick. All right. This one here. There's a problem in your book that talks about this one. Basically, if we know that the painter, Frank here, has a mass of 500 newtons, and he has 2 ropes that are tied to his swinging bosun chair, called bosun chair. And so each of these ropes would have a tension of 250 on each one, which would give a net force of 0, which means he's held up in the air. Now, unfortunately, this rope can only hold 300 newtons. And so, in this case, it's all right, because each of the 2 ropes attached to Frank's chair are doing 250, which puts them below the 300 Newton limit that they can support. However, if he ties off his rope to a flagpole, and now there's only 1 rope attached to his chair, we know that Frank weighs 500, so the tension on that 1 rope is also going to be 500. And guess what's happening to Frank pretty quickly? His rope is going to break, and he is going to go falling down splat, and he's going to be on workman's compensation, because he will not be able to work anymore. All right, because the net force is no longer 0 once the rope snaps. There's 500 Newton force pushing down, nothing to balance it anymore, because the rope no longer has tension pulling up on it, and he is crashing down below. All right, so that's all that. Now, another type of problem we can look at is like on a scaffold. All right, painters on a scaffold, and basically in this scaffold we have forces pushing down, which would be the weight of the objects. Let's just say that one man over here is 100, and if this one over here, we'll just say to make it easy, is also 100. All right, and we're going to say that there's a force of 200 on this rope. That's what's pulling up with a force of 200. And we're going to say the one over here is also pulling up with a force of 200. Okay? Now, if we know the scaffold is not going anywhere, we know that the net force must be 0. Okay? So, we know there's 200 force, 100 here and 100 here, the weight of the 2 painters pushing down, and there's 400 pushing up. So since it's not going anywhere, there needs to be another 200 newtons to balance that, and that would tell us that this board here must have a mass of 200 newtons. Now, that's probably a really heavy board unless it's made out of iron or something like that, but at any rate, that's what it would tell us. Anytime we have a scaffold that's sitting there, we know that the forces pulling up, the tension on the ropes, must equal to the weight or the force pushing down on the scaffold, which includes the board and the 2 painters. All right. Now, if one of the painters were to start walking toward the other end, then instead of being 200 and 200, this end now has more force pushing on it, so it might go up to, say, 300. Okay. And the one over here would only have, now, as he gets farther away, it's putting less force on it, so it might only have 100. But notice there's still an upward tension of 400 newtons, and you've still got the 2 painters and the board putting 400 newtons down, and so it's still at equilibrium. And finally, it may go off to completely the other end, where now you have maybe, say, 390 over here. Okay, and maybe only 10 newtons over here. But still, its net force is 0 because 400 pushing down, the tension on the ropes equals 400 pulling up, and they stay motionless because the net force is 0, therefore they are not going to be falling or moving and changing their momentum. All right, I hope that helps you out, and we'll talk to you later.